Hello and welcome back to my physics online video lecture supplement series. Today I wanted to begin the 7th set of lectures for my introductory physics courses, which is the set of lectures which are ultimately going to cover energy, conservation of energy, power, work, etc. And in today's particular video, I wanted to look at part one of this series of lectures, which is covering specifically work and energy. And so for us, the important definitions to know are both energy and work. And basically, we start with work, and that means the application of a force on some object along some particular path traveled by the object. In other words, I do work on something if I, for example, push on that thing and push it along a particular direction, so long as I am pushing in the same direction that the object is moving. And in turn, we can define energy as the ability of some object to do work. And oftentimes, not all the energy in a system actually is available to do work, but hypothetically, this is the maximum amount of work that the system could do under perfectly ideal circumstances. And we're going to look over the course of these lectures at two types of energy, broadly speaking. The first is kinetic energy, and the second is potential energy. And if you add these two types together, potential energy and kinetic energy, you get what's called the total mechanical energy of the system. And very often we end up treating that total mechanical energy of the system as being the energy of the system. For one thing, because in physics, it's usually the mechanical energy of a system that's converted into doing work. So I've already kind of hinted that there's several different forms of energy. The two big ones for us are going to be kinetic energy, which is the energy associated with the motion of an object. And kinetic energy, since there's two types of motion, and we've discussed two different types of motion, there's a translational and there's a rotational motion. Kinetic energy is therefore also has two types. There's translational kinetic energy and there's rotational kinetic energy. And we'll come back to rotational kinetic energy later. For now, today, I just want to look at the translational energy for the most part. The other type that is very important for doing basically mechanical energy wise is potential energy. And that is energy which is stored as a consequence of an object's position or configuration. And I actually list here a number of types of energy, although a number of these are not necessarily going to be discussed here. And in fact, you could debate whether chemical energy or nuclear energy or rest energy, for example, count as a type of potential energy, or whether it is fair to call those mechanical energy if we're going to define potential energy as a type of mechanical energy. They do depend, of course, on the configuration of your system. For example, the rest energy is contained in the amount of mass that an object has. So the more mass you have, the more rest energy you have. That comes from Einstein's famous E equals mc squared equation. But in particular, the ones that we're going to be interested in are the gravitational potential energy, and also the potential energy which is stored in a spring, for example, so elastic potential energy, and then electromagnetic energy. And of these, electromagnetic energy will be a topic covered in the second semester of physics. Gravitational potential energy we'll look at a little bit today, and then some more in the second part of this. And then, of course, there's thermal energy, which is basically heat. So this involves the transfer of energy from a hot object to a cold object, for example. So that's almost a brief survey of everything that I was going to talk about today. So now let's look at everything in a little more detail. And the first thing that we need to understand is work. And so work describes force which is applied along a particular path, be the path straight or be it curved. And I have down here a simple diagram which shows what work looks like, to the extent that that can be shown. Basically, if you're applying some constant force over some displacement, then the work done is going to be that force times the displacement times the cosine of the angle between force and displacement. So notice that this dashed line right here is parallel to the blue displacement line, and this dashed line, we could imagine a triangle being formed by drawing a second dashed line straight up here. So this is like the x and y components of this force. So since the box in this picture is being displaced along x, we only want the x component of the force, and that is the force times the cosine of theta, where theta is, again, this angle between the vector for force and the vector for displacement. And in fact, these are vectors for instantaneous force and instantaneous displacement, or even if you want instantaneous force and instantaneous velocity. But in the simple case, the displacement direction is constant, and so it's only a distance that's increasing, and then the force is constant. So in the simple case, what that means is that the work done on an object is the force times the distance that the object travels times the cosine of this angle between the two. You could also think of that again as the x component of the force times the change in x, where x is the particular axis along which this force is applied. So that's work in a nutshell, and so far we've looked at just sort of a simple sketch of what this would look like. Before I move on to a few more complex cases, I should mention what the units are. And so for us, the main unit, SI, is the joule. And so you can see here that work is force times a thing that is unitless times a distance. So the force is always in newtons if we're in SI. Distance is in meters. So a joule is the same thing as a newton times a meter. And if you review previous chapters' notes to get what units of force are, those are kilogram meters per second squared. Just remember F equals ma. So newtons must be the mass, which is kilograms, times the acceleration, which is meters per second squared. So our SI units, 1 joule is a newton meter, which is also a kilogram meter squared per second squared. In the US customary unit, it's just called a foot-pound. So our definition so far depends upon that force being constant. So force is, of course, a vector, and as such, it's going to have two components. One is the magnitude, the other is the direction, or you could think of it as force in X, force in Y. Of course, in 3D, that becomes 3 components because direction needs to have 2 components, and you could have X, Y, Z. So how we're going to define direction for the purpose of a constant force is that the force has a constant direction so long as the direction with respect to the object's actual motion is remaining constant. So for example, this box could go through 2 possible paths here. One is the straight path from here to here. One is the curved path from here to here. And so obviously if the box is moving in a straight line from here to here and we're pulling in this direction the entire time with the same amount of strength on our pull, the same magnitude of force, then this would be a constant pull force. So this is the simplest version of what constant force would mean. But look over here in this curved path. Intuitively, we might say the force is changing because the direction in which this thing is being pulled changes. But if you look at this path, you'll notice that everywhere along the curve, at least the 2 places where the box is actually drawn, the friction and the pull force both happen to be sort of tangential to this curve. Now, again, obviously, if this box is moving along a curve, that means that there must be some components to this pull force. One must be center directed because there's going to be some centripetal acceleration. But the relevant fact is that there is some component of this which is tangential to the curve everywhere and some that's perpendicular to the curve everywhere. The part that's perpendicular to the curve doesn't really matter for the purposes of work, because if it's perpendicular, that means that the angle theta is 90 degrees. So if we go back to the previous slide, then you can plug in 90 degrees here. Cosine of 90 is 0. So the part that is centripetal in this motion contributes no work. And you'll notice that the other part basically is tangential, and that tangential part is always has the same strength behind it, same magnitude. So that is effectively a constant force for the purpose of doing work, because at all points in this thing's motion, this component that we've labeled FP is parallel to the direction in which the box is being pulled. And so that counts as if it is a constant force. So in order to find how much work is done as this moves along this curved path, you'd basically need to figure out what this path length is, and you'd need to figure out what this parallel component of the force is, and also what the value of the friction is. And basically just multiply that parallel component times the path length and multiply friction times the path length. Subtract the 2 from each other, and that gets the net amount of work that's done. All right, so now let's do a few short examples. So first one is how much work is going to be done by lifting a 1 kilogram brick by a height of 2 meters on the Earth, or for that matter on the moon. Okay, so in order to lift a brick, lifting means basically overcoming gravity. So overcome gravity. And to do that, you basically have to apply the weight of the brick. So this basically means force is equal to Fg, which is the same as m times g. Okay, so that is how much force is actually needing to be applied. If you're lifting, you're applying that force basically upward. So here's force. We'll call this lift. And then this is also the direction in which we are moving. So this is the delta R direction. So this is lift. So these two are parallel, and therefore the work done must be lift times delta R. And parallel just basically means cosine of 0 degrees. So this is going to be mg delta R. And of course, delta R is also a delta Y or delta H. It's basically how high did we lift it. So work is going to be 1.0 kilograms times 9.8 meters per second squared times 2.0 meters. So all of that, if you multiply all these things together, 2 times 9.8 is 19.6 joules. So we have meters squared per second squared times kilograms. And so with correct number of significant figures, this becomes 20 joules. Okay, that's on the Earth. So this is for Earth. If we do the Moon, then G for the Moon is about 6 times smaller than G for the Earth. So we could basically just take this number and divide by 6. So W Moon is W Earth over 6. So we'll go ahead and put in the 19.6 joules, divide that thing by 6, and what we get about 3.27. So 3.27 joules. And again, we have 1 or 2 significant figures to work with. So this becomes 3.3 joules. Okay, so we've worked our first example here. Let's go look at the next example. Next example, how much work is done by carrying the above brick for 20 meters at a constant speed? Okay, so to do that example, let's think about what is involved in carrying the brick at a constant speed. If you're carrying at a constant speed, that means no acceleration. So acceleration equals 0, and that means that the net force on the brick must also be 0. So that immediately implies that the total work must also be 0. So total work is 0 joules. But if we want to make this question slightly more complex, we might say how much work is being done by the person who is carrying the brick. Okay, because gravity is acting on the brick, the guy is carrying the brick, both are applying a force. So it's also valid to ask how much work is done by a particular force. Well, let's draw a diagram of just the brick itself. And we'll draw the force that is being used to carry it. So F carry, which is also equal in magnitude to the gravitational force. And it's being carried 20 meters at a constant speed. Presumably it's being carried like across the room. So this would be delta X, about 20 meters. This right here, by the way, we had that it was a 1 kilogram brick, so this is going to be 9.8 newtons for what that's worth. All right, but notice now this is entirely in the y direction. So this could be written as 0, 9.8 newtons. This could be written as 20 meters, 0. So the two are in perpendicular directions. That means that our total work done by either one of these forces, we'll call the work by the carrying force, is going to be force carry times delta x times cosine of the angle between these two, and theta in this case is 90 degrees. So what that means is we have cosine of theta is equal to 0, and therefore the work done just by carrying it is also going to be 0. Again, the key phrase that we have here is that this is done at a constant speed. So that implies that the entire force that's being applied to the brick by the person carrying it is in the vertical direction. If it was not a constant speed, then gravity and this force would not entirely cancel out. That would imply that there'd be some component to this force which is in the x direction, and then some work is being done to the brick by this force. That's a kind of an important point that we'll come back to later on. All right, for this last example, we actually want to look at this picture of the guy who's trying to mow the lawn. And basically we're given that he's pushing on the lawnmower with a force of 120 newtons, and he's mowing a strip of grass that's 18 meters long, but he's not pushing straight forward on the lawnmower. The handle's kind of at some angle, so maybe he's pushing at an angle of 15 degrees. And so the question is, how much work is he going to do by mowing this lawn? Okay, so this angle right here is, again, 15 degrees. So the distance in question, 18.0 meters. The force in question was 120 newtons, and we use this work equals FD cosine theta. So that means that the work done should be 120 newtons times 18 meters times cosine of 15 degrees. So that is 2,086 joules. So again, three significant figures. We might write this as 2,090 joules, approximately. Okay. All right, so enough about just work for now. Let's move into the work energy theorem, or let's look at combining work and energy. So to do that, we can start with Newton's second law. Newton's second law, of course, is the one that says that the net force is the mass times the acceleration. And so that means that the net amount of work done on an object must be the mass times the acceleration, that's the force, times the displacement, or the distance over which this force is being applied, times this cosine of the angle between the instantaneous displacement and the instantaneous force. And so all of this simplifies out to basically mass times acceleration in the x direction times displacement in the x direction. And you know, if you don't want to draw so that you're going in a straight line along a particular axis, then you'd have to have m times a of x times delta x, and then plus m a sub y delta y. In any case, you can recall from the kinematic stuff that we had this time-free equation, which basically related acceleration times distance to the final and initial speeds of an object. And again, assuming a constant acceleration, which is, you know, we're still assuming a constant force, therefore we have a constant acceleration. So that means that the net amount of work done, if you basically substitute this into this equation, is going to look like 1/2 times the mass times the difference in squares of the speeds. So let's look at that for a second. So again, kinematics gave us that for constant acceleration, we can write 2a sub x delta x equals v final x squared minus v initial x squared. Okay, so in a 1D motion, this basically would be written as basically like a 2a delta x is v final squared minus v initial squared. Okay, and then we also have that the net amount of work done to an object is mass times acceleration times distance. Okay, so if you solve this thing over here for the a delta x term, because that's in both of these equations, this is basically saying a delta x is equal to 1/2 v final squared minus 1/2 v initial squared. All right, so now go ahead and plug this right here into the work equation, and what you end up with is that the net work done is the mass times 1/2 of the final speed squared minus 1/2 of the initial speed squared. And so this also is the same thing as saying 1/2 times m times the final speed squared minus 1/2 times m times the initial speed squared. Okay, so that's where that latter equation was coming from. All right, so I mentioned before that kinetic energy is the energy associated with the motion of an object. And here we have some terms that are very obviously associated with translational motion. So it follows basically that the kinetic energy of an object might be given by 1/2 times the mass times the speed squared of the object. And so this right here is basically saying that the net work done is equal to the final kinetic energy minus the initial kinetic energy. And so this is sometimes called work energy theorem or work kinetic energy theorem. And again, this also could be used to change the rotational energy of an object or system rather than the translational kinetic energy. However, we have not yet covered the rotational dynamics that we need to understand how we might be changing the rotational kinetic energy. So for right now, I'm going to limit us to just looking at translational kinetic energy. Okay, so let's look at some ramifications of this work energy theorem, and then we'll look again at kinetic energy in a little more detail. So the work energy theorem just says that work done to an object should equal the change in that object's energy. And more often we look at that in terms of the object's kinetic energy, specifically because of things like that derivation that I just did. So the net amount of work should be the change in the object's kinetic energy. And if therefore we have a net work that's positive, that usually means the object's speed is increasing, the object's kinetic energy is increasing. If the net work is negative, then the object's speed will decrease and the object's kinetic energy will decrease. So what does this actually mean as far as a positive amount of work versus a negative amount of work? Basically, if we go back to the diagrams that we've drawn earlier, for example, this one in which we have a lady who's pulling on a box across the floor. A positive amount of work basically means that you are pulling with some component that's in the same direction as the box is going to move in. Okay, you can also imagine, though, maybe the box is initially actually sliding in this direction. So it's going the opposite direction that she's pulling on it, and she's basically trying to stop the box. So that would be sort of doing a negative amount of work on the box, or if you want, you could even think of it as the box is doing work on her. That's basically just an application of Newton's law, Newton's third law specifically. So if you're pulling on an object in the same direction as the object is moving, then you will tend to increase the object's speed. If you're pulling on it in the opposite direction from the way the object is moving, then the object's speed will decrease, and that sort of defines whether you've done a positive or a negative amount of work on the object. So far this actually in some ways is just a logical application of the material that we've covered so far, in particular of Newton's laws and of kinematics. And if you have a situation in which the net work is zero, the part of the implication is basically that you're in a Newton's first law regime. So, for example, we talked about lifting an object, we talked earlier about carrying an object. And in that case, we really were in Newton's first law regime because we had gravity pulling downward on the object and then the person lifting upwards on the object, and those two forces were exactly in the opposite direction, and they canceled each other exactly. Technically, any given force can do zero work as long as it's perpendicular to the direction in which the object is moving. But again, bear in mind that except for in one case, if you have a force that is always perpendicular to the object's motion, and that force is doing zero work as a result, there's usually a second force that is opposing the first force. The one exception to this rule is if you have some sort of rotational motion, for example, the uniform circular motion. So this is the one exception that we're really going to encounter in this class. And again, that force is still doing zero work, but it's not necessarily a force that is opposed by anything. So there is an exception to this rule that says if the network is zero, then Newton's first law applies. You can be going around a curve or on a circular motion. But in any case in which the net work done to an object is zero and the object is not turning, the implication is that there must be several forces at play to sort of balance the system. In other words, I can push on a box across the floor and apply some work to that box and therefore have a non-zero work that I am doing, but I may be pushing against friction. That means that friction is pushing in the opposite direction, and if friction is equal to the amount of force that I'm applying to the box, then I'll get zero work. I can also, of course, push downwards on the block while it's moving across the floor, in which case I'm not doing any work to the block because my force is perpendicular to the direction in which the block is moving. But that force is also being balanced out by the normal force, just as there's gravity acting on the block as it's moving across the floor, and just as that is being balanced out by the normal force. Okay, let's look at kinetic energy at this point. So I kind of sort of defined it for translational motion as an equation before, but what actually is kinetic energy? Well, kinetic energy is basically the energy that's associated with the motion of an object. And you can think of it in two ways, really. The standard way of thinking of it, the traditional way, basically, is how much work is the object going to do in coming to a stop. So, for example, imagine that you have a block which is sliding across a frictionless surface. And if that block needs to be brought to a stop, it can push against some other object. How much work will it do pushing against that other object by the time that it comes to a complete stop? An easier way of thinking of it would be, how much work do you need to do against the motion of some object in order to stop that object? And these two conceptual pictures are both assuming that you're not heating or deforming or breaking or anything like that the object as you're bringing it to a stop. And I should add a third way of thinking of this, which is sort of the reverse of all these other two, which is that you can think of the kinetic energy as being sort of like the amount of work that is needed in order to take the object from rest to moving at the particular speed that it's moving at. So how much work do you need to do if the object is already stopped and you want it to get to some final speed? That is also equal to the kinetic energy. Regardless of what method we use to picture work, the SI unit is going to be the joule. So work and energy both have common units, which is the joule. And we've already discussed what a joule breaks down to, so I'm not going to recap that here. The equation that is associated with translational kinetic energy is that the translational kinetic energy is half of the object's mass times the object's speed squared. Notice that like work, energy is a scalar term. And I should add here that this kinetic energy term, this translational kinetic energy term, is generally associated with a single object which is moving. If you have more than one object, then you can just keep adding a half of the mass of the next object times the speed squared of the next object, etc. But usually when you get to a very complex system, such as figuring out what kind of kinetic energy you have in a gas, you can associate this translational kinetic energy with the temperature of the gas. And so temperature actually can be thought of as a measure of the average translational kinetic energy of the molecules in the gas. Okay, so that is translational kinetic energy. I keep mentioning rotational kinetic energy. This equation is not going to really mean much to most of you, but for completeness, I'll go ahead and put it up here. The rotational kinetic energy is given by half of what's called the moment of inertia times the angular speed squared. So by now you've been through the lectures on rotational kinematics, so you're familiar with this omega term is the rotational speed of the object. The I term is called rotational inertia, and we're going to look at it in the future when we talk more about rotational dynamics. Basically, it's a combination of how much mass the object has and then how that mass is distributed. So it's usually some function of mass and distance from axis of rotation. And for completeness, this is often combined with translational kinetic energy because you can have stuff like rolling without slipping, which we talked about in a previous example. You can also have a mass which is falling and connected to a large flywheel. So for example, as this mass falls, it's going to be picking up kinetic energy in exchange for losing some, basically potential energy, which we'll talk about in a minute. Gravity is working on this mass as it falls. That's going to cause it to increase its speed, increase its kinetic energy. But in order to do that, it also has to make this flywheel spin. So if this flywheel is large, then the rate at which this thing falls is going to be substantially decreased as compared with a very small flywheel. We'll look at that in a future lecture. Let's do a few more examples before moving on to talk about the potential energy. So, first example, how much kinetic energy does a 90 kilogram man have if he's running at 5 meters per second? All right, well, the kinetic energy is given by 1/2 times mass times speed squared. Now, the important thing is that we need to have mass in kilograms, which we do, and we need to have speed in meters per second, which we do. You need both of those to be in those units if you want your energy to come out as joules. Because again, a joule is a kilogram times a meter squared per second squared. So this one is therefore going to be a pretty straightforward problem. We basically go 1/2 times 90 kilograms times 5.0 meters per second. We have to square that 5.0. So that means that the total energy is 1,125 joules. And we should probably round it off to 2 significant figures. So the actual kinetic energy when keeping track of significant figures becomes 1,100 joules. Okay, so let's look at the next example then. So the next example has to do with the 9x19 parabellum bullet. This, by the way, is one of the most popular types of handgun ammunition, if not the most popular. So the question is, if we assume 7.45 grams and a speed of 390 meters per second, these are some typical values for this bullet, how much work is needed to actually stop the bullet, assuming again that you're not doing anything like heating or that kind of thing. All right, so work should be equal to change in kinetic energy. And the change in kinetic energy in this case, that basically means 1/2 m times v final squared minus 1/2 times the mass times the initial speed squared. This term right here, we're trying to stop the speeding bullet. So this term is actually 0. And so that means that the work should be 1/2 times the mass times the initial speed squared. It's going to be a negative because it is being used to slow or stop the object. And this is what I was talking about earlier in this video. Actually, the last example. This is the mass, 7.45 grams. We actually need to convert that mass into kilograms. So this right here becomes 1/2 times 0.00745 kilograms rather than 7.45 grams. And that's times 390 meters per second, and this latter one is squared. So that means that the total work needed to stop a speeding bullet is about 573 joules. And again, we can write that as a negative because it is being used to stop an object which is already moving. Okay, and so follow-up question to that previous question. Suppose that the target that this bullet stops inside is such that the bullet travels for 5 centimeters within the target before stopping. So the question is, how much force is being exerted on the target? And we're going to assume, for simplicity, that we don't need to account for any force or any work that's needed to deform the target, deform the bullet, etc. Okay, so again, we can use that work is going to be change in the kinetic energy. And in that previous problem, we found that that was 573 joules, roughly. So the question is, assuming that this occurs over 0.05 meters, how much force is needed? Well, work is going to be force times the distance times the cosine of the angle between the two. And we're basically going to make the assumption that as this bullet is basically burrowing into whatever the target is, that there's some frictional force like this from the, for lack of a better word, walls of the hole that the bullet is boring into the target. And then also some force maybe from this solid part of the target that the bullet is having to break through. And all of those forces are basically going to be directed in the opposite direction that the bullet is moving in. So with that being said, that means that theta is going to be equal to 0 degrees, and so we can write work is force times delta x. Now the delta x is the stopping distance, 0.05 meters. So we can solve this thing for force by taking work, dividing it by delta x. So we can say basically 573 joules divided by 0.05 meters. And so what that's going to get us is a total force of about 11,468. So let's say 11,500 newtons. So that's how much force is basically being applied to the bullet in order to stop the bullet, and therefore that's also how much force by Newton's third law the bullet must be applying to the target. So the potential energy is the next thing that I wanted to talk about, and it's actually going to get a little bit more thorough treatment in the next part of these lectures. But for the sake of giving some definition to it for now, we're going to define potential energy as the potential for a force to do work on an object. And so this is applicable to what would be called a conservative force. Conservative forces are forces like gravity or the electromagnetic force, or the force that's being held by a spring under tension or under compression. Basically, the conservative forces are forces that the path length that you take to get from point A to point B don't matter. But the non-conservative forces are going to be things like a propulsive force, like a person who's actually pushing on a box, or the propulsion from a rocket, from the back end of a rocket, and it's also dissipative forces like friction. So potential energy is associated with things like gravity and springs and electromagnetism, but not with external forces like a person pushing or a rocket or friction, etc. And So you could think then of potential energy as being how much energy has been stored in an object based on the position of the object. So this position, in order to really define a position, again, recall that you need to have some coordinate system. And a coordinate system really only starts to make sense if you have more than one object. So usually it will be something like the position of the object which has potential energy with respect to, say, the Earth. Or maybe it's the position with respect to the equilibrium position of a spring, etc. And so if you have a single isolated object which is taken apart from an entire system, it really doesn't make sense to say that that object has potential energy. You can only really have potential energy within a system of some sort. So about conservative forces. What a conservative force is it's a force that is going to do the same amount of work to an object based on the starting position and the end position, regardless of how that object gets from start to end. So we have here a basically picture of a girl who is given a choice. She can climb up a ladder and then she can either go down a slide or she can jump off the springboard. And either way, she ends up in the same pool below. And so her change in height is the same regardless of whether she dives off the ladder or whether she slides down the slide. In both cases, it's going to be from here to here, from this height to this height. And so gravity in this case is going to do the same amount of work on her, whether she goes this way or whether she goes this way. And so that means that gravity is a type of conservative force. Basically, if you do work against a conservative force, you can recover that work in the form of kinetic energy. In other words, she did work against gravity by climbing up this ladder. So she climbs the ladder, she's up here, she had to work against gravity to do that. Her speed hasn't changed, but that energy has been stored by the fact that she is higher up than she started from. Then if she steps off of the ladder, she's going to, even if she just simply steps up, she'll start speeding up, speeding up, speeding up, speeding up, speeding up, and she'll hit the water. And she'll hit the water with the same speed, whether she steps off the ladder here or whether she steps down the slide here and slides down the slide here, assuming it's a frictionless slide, of course. So that's another way of seeing that gravity is in fact a conservative force. It doesn't matter whether she slides down this slide, whether she bounces off of this diving board, etc. So let's look for contrast at what a non-conservative force would be like. A non-conservative force is a force that is going to do a different amount of work depending upon the path that an object is traveling around. So look here at this book on the table. There's going to be friction between the table and the book. And you can move the book from point A to point D in a variety of different paths. If you move the book from point A to point D along the blue line, then friction does not really act against it save for this short distance. If you move along the red path, then friction is acting against it this entire time. So you have, assuming this is a square, 3 times more distance over which the same amount of friction is working, and therefore 3 times the work done by friction if you take the red path than if you take the blue path. So friction is not a conservative force. That means that, among other things, you lose energy to friction and you can't really recover it. Not mechanically anyway. I mean, the energy is lost in the sense of that it might heat the table, it might cause some minor deformation to the book or the table, etc. But it's, as far as being usable energy, it's effectively gone from the system. It goes into other types of energy that are sort of waste, if you will. And because friction depends upon what path you take to get from point A to point D, there isn't really any kind of potential energy function that we can just associate with friction. It doesn't make sense to say, well, since the distance is a meter here, and since the coefficient of friction is so much and the weight of the book is so much, therefore the potential energy is 1 meter times the weight times the gravitational acceleration times the coefficient. No, that's nonsense, because the book doesn't necessarily go from here to here in a single straight line. So there's a variety of non-conservative forces, and by the way, we assumed here, I kind of planted the assumption that it's always lost energy that's done by a non-conservative force. That's not always true. For example, a propulsive force is also not really a conservative force. For example, I could be pushing the book along either one of these paths, and if I push it along this path with the same force as I push along this path, and assuming that I'm pushing with the same component in the direction that the book is traveling at all times, I will do more work on the book here. Therefore, the book will have gained more energy than going from here to here. So the major types of non-conservative force that we'll deal with more directly, or that we could in principle deal with more directly as mechanical work, is basically going to be from propulsive force, from drag, from friction, from my pushing on the object, etc. So that is all I wanted to cover in the first part of this lecture. So I hope that you enjoyed watching this video and that you're going to find it helpful. I look forward to some of the questions that it may generate for in-class discussion, and thanks for watching.